So I said this was a combined example and exercise, so I'll provide a hint for one way to proceed. So if we consider the chains of M with this twisting by the Stiefel-Whitney class, then by definition this is the chains of the universal cover tensored over Z pi 1 with Z omega. Now, as I said before, we can simplify this a little bit by thinking of how Z pi 1 acts on both sides and identifying these actions. Any orientable loop in pi 1 acts trivially on Z because the Stiefel-Whitney class maps it to 1. So this action, this trivial action on the right, should be trivial on the left. So in tensoring over Z pi 1, we're effectively quotienting out by the action of these trivial loops on the universal cover. What this does is, when we quotient out by all the loops in the kernel of the Stiefel-Whitney class, this takes us to just the chains of the orientation double cover. So let's write that down. This is the same as chains in the orientation double cover, now tensored over ZZ mod 2 with a ZZ mod 2 module, which I'm calling Z minus. This is where Z minus is the ZZ2 module given by, well, Z2 acts as minus 1, on the integers. So the exercise will be to finish this example off from there. And now in Andrew's book there are several formulations of Poincaré duality. I'll talk a little bit about what he calls twisted Poincaré duality, and also the slightly more general universal Poincaré duality. So I've already written up on the board the statement of twisted Poincaré duality, and that says that if you've got a compact connected boundaryless manifold, then this homology twisted by the Stiefel-Whitney class is in the top dimension isomorphic to Z. And if we take a generator, we can call this a twisted fundamental class, and then capping with this class gives an isomorphism from cohomology twisted by omega to untwisted homology, or from untwisted cohomology to twisted homology. And these are isomorphisms in each case. Now we can have a statement of Poincaré duality for something slightly more general if we have any oriented cover of M. So thinking what we did in the example there, we were quotienting out by loops in the kernel of the Stiefel-Whitney class. And if we quotient out by all of them, then we end up with chains in the orientation double cover. But if we quotient out by, say, part of the kernel and not the whole thing, we end up with a different orientation cover, which is between the universal cover and the orientation double cover. So we just have another oriented cover in between. So in particular, this will have a group of covering transformations pi for some pi between pi 1 of M and pi 1 quotient out by the kernel of omega. So for any such pi, there's a corresponding cover, and there's a corresponding Poincaré duality theorem for this cover, which is called universal Poincaré duality. And for a statement of that theorem, I'll just point you to Andrew's book in chapter 4. So it's just worth saying that this can be done a bit more generally. And now for the final section of this talk, we'll return to handle decompositions like we were talking about in the first lecture, and this time we'll consider them as we'll consider the handle chain complex as a Z pi 1 module chain complex. So we saw in the first lecture, if we have a cobordism, this via a Morse function gives us a handle. So via a Morse function we get a handle decomposition. And to this handle decomposition we associate a Z pi 1 module handle chain complex, and we associate this is effectively just taking coefficients in Z pi 1. So we write this C star W rel M with coefficients Z pi 1 of M, of W rather. And viewing the handle decomposition upside down, or switching our Morse function to minus the Morse function, we also have rel the other boundary component. So now let's explain how we get a chain complex over Z pi 1. So suppose we have two embedded spheres, so Si and Sm minus I, embedded in W of dimension M. Then, just due to their dimensions, generically, Si intersects Sm minus I in a discrete set, and transversely. We can perturb this to be a transverse intersection, which I denote with this symbol. And then to each point in the intersection, we can associate a sign, which I'm going to call epsilon of P, either plus or minus 1. And we do this as follows. We say well, we choose orientations for W, S, I and Sm minus I, and then we say that the point gets sign plus 1 if the orientation of tangent space at P of Si, direct sum tangent space at P of Sm minus I, if the orientation of that matches the orientation of W. So TP of W. So it can either match or it can not, and if it doesn't, we give it a -1 otherwise. And then we can take the sum of all these signs over all points in the intersection, and we call this the intersection number. And this can be shown to be independent of choice of orientations. So quickly an example. Suppose we have R2 and we have two embedded sphere circles. So here's S1 and here's S2 minus 1. They intersect in 2 points. We orient R2, so all over we have these little frames, and we orient our circles. So let's orient this one this way and this one this way. And so if we consider this first dotted with 2 minus 1, then what we do is we put the orientation of this first and then the orientation of this second, and we see that this is the other way round to the orientation of R2. So here we get -1, whereas down at this point, when we put this one first and this one second, just rotating this around, we've got the same orientation as we had for R2, so we get a sign of +1 here. So if we then look at the intersection number, we sum these two and we get 1 minus 1 is 0. And this is telling us that actually generically we can perturb these so that they don't intersect at all.